Okay, we're going to have a look at polymers as I wrote in sector. I think hopefully you've looked at it. We're going to do the last whole topic out of order. So we're going to do the last part, 4.4, which is about materials. We're going to do that first because that will include the stuff that we use for the prac. So fingers crossed everything will go all right. Next week we'll be able to get close to starting some of that stuff for the second prac and get that done. So the first part, though, is about polymers, and polymers are probably a good place to go next anyway because it relates fairly heavily to the organic stuff that we were looking at last term. I'm just going to use the diagrams and stuff from SASTA just because it's a whole lot easier, and that way you can access any of the notes that are there within that book. But obviously look through the essentials as well, and that'll have different explanations and different examples. So the stuff in here, the stuff that's in that orange box, they're the SACE things that we have to do. So the first part is about saying that polymers are made up of smaller molecules, and we call them the monomer. And what we're going to talk about really is that the polymers are produced in two ways. One is by using what we call addition, and one is by condensation. Okay, the addition is sort of new. Condensation is just the same things that we were doing in the organic topic with polyesters and polyamides, so ester linkages and amide linkages. So in terms of the chemistry, there's not a lot of new stuff in here at all. So the dot points say identify whether a molecule could undergo polymerization by looking at structural formula. So could it actually form a polymer? Okay, and if so, what type of polymer? Whether it be addition or condensation. And then if you've got a polymer, identify it being a product of addition or condensation. So if you've got a polymer, how was it formed? By addition or condensation? And can you identify the repeating unit of a polymer? Okay, if you've given it structural formula. So the first part here, the addition, which is slightly new, but really not that hard to comprehend, I don't think, is really we're looking at monomers, okay, the starting molecule, as being double bonded carbons. Okay, so we've got the example of what's called vinyl chloride. All right, now that follows a different naming system slightly, but you can see that it looks very much like ethene. Okay, double bonded carbons, but has a chlorine molecule replacing one of the hydrogens. Okay, you're not going to have to name that or anything, but you might be given that. But what's important is that we have this double bond here. Okay, and so what can happen, you could imagine, is if we broke that double bond, and we can't just break it by itself, but let's just imagine we did, which is sort of not really true. It doesn't exist like that by itself, but in a reaction that can happen. What that means, though, is we have a spot right here, okay, where there's a bond missing, where there's an electron that sort of would like to pair up with another electron. Okay, and obviously if we had the same sort of thing happening over here, that should have been a Cl. I've written them wrong, I don't want to confuse you, so there, like that. If I was to do the same thing over here, and let's put the Cl there, okay, then we would have another spot here, okay, and so ultimately we can form a bond in that space. Okay, the same thing then is happening over here and over here. Okay, so we can just keep that process going and going and going. What you notice is we haven't had to add any new atoms. There's no new atoms that have come in. There's nothing else that's been involved with it. If you look at the equation has sort of drawn here with structures, you've just got two of the vinyl chloride monomers combining. Okay, and in reality, you could have thousands of them, and that's what polymers are made up, thousands and thousands of these monomers joined together, but effectively nothing else. Okay, this reaction's done at 13 atmospheres and not that hot, 50 to 75 degrees Celsius, but effectively that is it. Put them together, they combine and create this long chain that we call polyvinyl chloride, and perhaps you would recognise that as being PVC. Okay, very common monomer, very common polymer. Sorry. So what's drawn over in this section over here? This section is a longer chain of the polyvinyl chloride. The dotted ends to it, they just represent it keeps going. What's been done is that these brackets here, they've been put in to show what is the repeating unit. Okay, that just keeps repeating, and the little n just says, well, there's multiple of them. Okay, so you might have to draw the brackets around something in a structure to show that that's happening. Another example below has the same sort of thing, just a slightly different molecule. Okay, doesn't matter what it's called, but you can see perhaps you would have been given this, okay, and you had to look at it and say, okay, well, the only way that this could have been made would have been from a double bonded addition reaction. Okay, there's no amide links, there's no ester links. Okay, they're the only other things you'll be looking for in this polymer section. There's none in there, so the only thing it could have come from was addition. So, therefore, in this little space here, the monomer must have had the double bond. Okay, so you may well have had to come up with that structure from this. Okay, so that could be certainly a question that could be asked. The other example of the condensation ones, so rather than go through a whole lot, this is just a table from the textbook, basically looking at either polyesters or polyamides. Okay, where that's what we're looking for. But when we have a polyester or a polyamide, when we make our examples, we could have two things happening. So the two examples that are shown there for the polyesters, the first one has a dialcohol and a dicarboxylic acid. So we have the dicarboxylic acid here, which has two carboxylic acids, one on each end, and then we have the diol, which has the two alcohols, and so we can imagine that we can get a ester link happening here, and then this sort of molecule that's created just from that little reaction will still have that carboxylic acid at that end and that alcohol at that end, okay, and then we can add more. Okay, so at this end over here, we could add another one of these into this space, and that process just continues. Okay, so we get the polyester that has those two things in it. Remembering these are condensation reactions. When we do it, we are losing this OH and this H, okay, to cause that bond, which means we're going to have water left over. Okay, so water is released. It's a condensation reaction. All right. The other option, rather than having the dicarboxylic acid and the diol, would be just to have one molecule that has the carboxylic acid at one end and a alcohol at the other end. Okay, so that's another option. Then you just have that one monomer that just keeps going rather than having two monomers. Okay, so they're the possibilities. The polyamides, exactly the same idea. Okay, you could have the diamine, so one on each end, plus your dicarboxylic acid, or you can have one that has the amine and the carboxylic acid, okay, on the same molecule. Remembering, once again, the polyamides are condensation reactions. They produce water. Okay, so that's the first part. we'll probably break this video into two. I'll do another little bit, then we'll stop, just to make it easier for uploading, and do a second part. But we'll have a look at this bit first, and that is that we can make polymers synthetically, so we can do them make them in a laboratory, if you like, factory, realistically, to create polymers that have all sorts of properties. And so we want to think about what the properties of polymers are and what are the advantages and disadvantages of those synthetic polymers. So realistically, it's just looking at the table of advantages, disadvantages, really. So the advantage of these synthetic ones is that they're versatile. You can make all sorts of different polymers, and they have different applications. So we know that plastics, even just thinking about plastic, we have different versions of plastic, very hard plastics. We have Glad wrap. We have very, very light but strong plastics. We have very flexible ones, all sorts of things like that. So that's an advantage. They're very versatile. They often have, or we can create them to have the chemical and physical properties that we want. Okay, so some things we know about plastics that are often bad is that they degrade in sunlight. We can certainly put properties in that help them to be more UV stabilised. We can make them stronger, lighter, see-through, coloured, all these sorts of things as well. Okay, and realistically, on the industrial scale, they're cheap to make. Okay, so that once we've got the factory set up, the chemical reaction set up, it's cheap to make those things. The disadvantages are, one is that the synthetic ones are basically all derived from petroleum, so it's a non-renewable resource. Okay, so there's obviously issues with that. And secondly, as we know, that the being biodegradable is a problem. So the addition polymers, they don't biodegrade. So we have this big problem that they hang around. We know there's lots of issues with pollution of those sorts of things. Okay, so I'm going to stop that video now, and I'll put a part 2 up later in a minute.